ahead and click and say welcome everyone on this Saturday. I appreciate you all taking the time to be here. We'll go ahead and get started. Agenda, we're going to do a quick recap of the summer goals and activities. Then we're going to jump right into the nitinol activity. If you didn't get your nitinol yet, it should be coming very soon. I mailed it on Tuesday. No worries, you'll be able to work through today and test it out next week. It's a very simple but powerful activity. And then we're going to hear from some teachers who already did implementations, and they're going to share with us kind of what that experience was, and maybe for those of you that haven't implemented, might give you some thoughts or ideas, or you're welcome to get advice. Then hopefully we'll have a little bit of time at the end for any questions about future implementations or anything else you want to share. But we will be promptly ending at 11. So as always, you know, I like to do the land acknowledgement, so I think it's important, but you've all seen it, knowing that the Ohlone tribe are the indigenous people at Stanford. So I won't play the video for you again since you already saw it, but I just like to acknowledge that. All right, so the fun part. What is something that happened this past week that made you smile? So if anyone wants to share something that made them smile this week, you can type it in the chat, or of course, we'd love to hear your voice as well. And I want to hear from at least 2 people before we move on. Oh, someone already had their first snow day, or a first snow and a 2-hour delay. Oh, yikes. Snow. I'm afraid of snow. Town Christmas parade. Oh my gosh, that sounds lovely. Oh, and Gabby went for a run. Wow. Running. That's amazing. Got to see family from Japan. Oh, that's wonderful. So it sounds like everyone's really getting a chance to enjoy that break that we all just came off of. So important, right? All the energy that you put into your students, you need to make sure that you give that energy back to yourself and your family. Ooh, photo shoot, Sheena. Sheena, very interesting. Basketball season, yeah. So many good things. Well, that's wonderful. I'm glad to hear these things that made you smile. Recapping last summer, if you were here at Stanford, this side belongs to you, right? Got to walk you around the campus, got to use the SEM physically as well as virtually, and then of course the cards that were a new activity, visiting our clean room. If you were virtual, you got to hear from some amazing talks from partner sites and use the SEM virtually to see how it worked, and we got to spend time together and see lots of fun activities. So altogether, that means that 52 teachers last summer from 17 states got to join our Nano educator community. So this is a really wonderful group of teachers. I try to send you those monthly emails, so I'm not spamming you, of interesting things that are related to Nano and opportunities for both you and your students. So please take a look for those. So far this school year, more than 2,000 students have done a Nano lesson based on these 52 teachers. So those of you that implemented are really contributing to that number. It's amazing to me, right? The power of one teacher and how many students we can interact with and influence. It's just amazing. So I just thought it'd be great just to remember that we are spread across the country and a powerful group. So if you're just curious how things have changed, one of the things is, wow, you guys are killing it, your cohort. You're very close to the total from all of last year's teachers. So you are on pace to break records this year as far as doing Nano with your students, which I think is amazing. So you're already here and it's not even December. One of the things you will be seeing from me is, even after your first year, you will still be connected to me, hopefully, where I will ask you the following year, hey, are you continuing to do Nano and how many students? And so we call those our alum. So if you happen to move school districts or your personal email changes and you want to stay connected, please send me an email so that I know that and I can update, my list to keep in touch with you. All right, so what did we do last summer? Well, you got some awesome professional development. an opportunity to figure out how to put it into your classroom. And now we're continuing that support. So I think that's really one of the delineators of this program from other programs is we want to stay connected to you. We want to continue to provide you with support. So if there's anything that I can do to help or you have a question, you know, you're always free to email me. I try my best to respond to you within a few days. You are really some of my top priorities as far as emails that I need to respond to. A reminder about our nano story, right? We know it's very small, which makes very unique properties, lots of applications because of this, and we need, special tools to be able to see that. And this is all connected to the big idea that nanoscience is an important field of modern technology that touches on all different areas of science. So if you've forgotten a little bit about your nano, I do like to remind you what's special, right? High surface area to volume, allows for miniaturization, similar scale to biological molecules and structures. Wave properties are really important. Love that chocolate lithography, right? And of course, the topic we didn't touch too much on, which was the quantum mechanical effects. So, we can make gold nanoparticles of really any color that we want, leveraging, the optical properties that change at the nanoscale. Reminder about fabrication, because, right, we have to make these things. So we have that top-down fabrication where you're chiseling away material, and then you have the bottom-up where you're putting it all together, and it self-assembles. Okay, so those are the two main types of fabrication. When we're talking about clean room, we're usually talking about top-down, right? We're chiseling away, adding a little bit, chiseling away. Okay, that's why we need those big tools. When we're talking about bottom-up, that's usually chemistry. We're putting things together in the right concentrations at the right temperatures, and then that sets up self-assembly to happen. All right, so some of the activities that we provided you supplies for, of course, good old Sunprint kit for modeling fabrication in terms of lithography. The thin films with the nail polish, which several people did as an introduction with students. The magic sand, some of my favorite. Alka-Seltzer for looking at surface area to volume, of course, the chocolate lithography. So just thinking about, have you had an opportunity to do any of these activities, or are you currently thinking about, oh, this one I think is going to fit great in this piece? And this is an opportunity, to get some guidance on that if you like. So in the chat, if you want to drop in, if you've done one, what you did and your favorite was, or if you're thinking about doing one, what is the one you're thinking about doing? And so we can see and notice I intentionally left off the card sort. So the card sort is sort of the simplest one that a lot of people do in the beginning. I'm leaving that one off because I like it to be a little more lab oriented. So I'm curious, what people are thinking in terms of, labs that actually are going to be hands-on for students to do. And then we'll see what we're all saying. Ooh, Jennifer, that's right. Various educators. I love that you all share stories of sharing with other educators what you learned at the workshop last summer. So that's wonderful to hear that you're spreading the nano love. Okay, yeah, SEM definitely, and we'll talk about that. If you're interested in doing the SEM and getting remote use, Hitachi's been really, really non-responsive this year, and that the RAIN network is the way to go. So those can definitely be things we can talk about more toward the end. I see lots of magic sand, which I love. Magic sand is really, really easy to use. Oh, yeah, okay, good call. Requesting for a link to the resource document. That's a great point. I'll dig that up when we have a quick break where I'm not speaking, and I'll put that in the chat for sure. Or if Krithika or Jenny or anyone else has that handy, if you want to share the resource document. And we actually have two, right? We have the one for the in-person teachers and the one for the virtual teachers. Most of it is similar, but some of the talks will be different. And you're welcome to look at both. So we'll make sure to include both of them, but that's a great suggestion. Thank you. All right. So if you received your materials, you got another one of these if you haven't gotten one yet. So remember this, right? Depending on which version of the workshop you took, we might have spent more time talking about this, but this is a really simple way to introduce students to microscopy and thinking about how you can get information about something that you can't see. And you can do it with any magnet that you like. So for this workshop, we're not going to spend a lot of time on it. Anyone want to give a quick summary of what they remember or what they thought or what they used with this, rather than having me talk about it? Oh, and I forgot to mention, of course, I will be giving you this slide link. So don't worry about that.
If it's okay, I can talk about this. This is Nicole.
Oh yeah, please, Nicole, share with us.
I recently did this lesson. So I found out that my 7th and 8th graders have never used a microscope before. So they didn't have science teachers for the last couple of years. They just had a bunch of substitutes. So we dusted off the optical light microscopes and I set up a workshop with University of San Diego so we could work with the SEM. So yeah, it was really cool because the kids had no prior knowledge, so everything was brand new. So they immediately noticed that with the optical light microscope, it has to be a very thin sliver and the light has to travel through the specimen. Whereas with the scanning electron microscope, the electrons bounce off the surface. So you get more of a surface view of the specimen. And they also just learned that the SEM microscope, because we had also done the card sort, we were looking at measurement and we were learning about positive and negative exponents in terms of measurement. So the size of the specimen and magnification became very apparent for them. So they were like, oh, wow, we're able to zoom to extremely high powers with the electron microscopes. And they also noticed with the optical microscopes, you could see in color, whereas the electron microscopes, you can only see in black and white. And then we were able to really explore nanostructures. So when we did the card sort, I introduced the concept of like the nano world. And they're like, oh my gosh. So like the butterfly wing was one they could really relate to. And then we were able to really zoom in and look at the nanostructures and talk about how that might impact the color and what you see of the butterfly as it like flutters past you.
That's awesome. Thank you so much for sharing, Nicole. Nicole tapped into the RAIN network, which UC San Diego was part of it. So you don't have to live in California to use the UC San Diego RAIN net, which is part of that RAIN network, which goes across the country because it's virtual. So San Diego just happens to be one of the sites that's very good about interacting with teachers. So great example of how you can use, the resources that you've learned about in the workshop to bring some really amazing things to students, especially Nicole, students that haven't even had a light microscope by middle school. That's heartbreaking. So I'm so glad that you did that for them. That's amazing. All right, thank you for sharing. So I just found the resource page for the virtual teachers. So I just dropped that in the chat, and then I will find the one for the in-person teachers, and I'll put that in there as well. All right, great. So when you get this slide deck link, this will have a link to slides that walk you through sort of probing what you can't see. And so it talks about magnetic poles and gives you some information about having them guess what the surface looks like, and then has some pictures of like what an AFM tool looks like, and then happens to bring up the butterfly like Nicole mentioned and how it's different in different sorts. So you have access to that slide deck. It's on the resource page, I believe, as well, but it's also right here. And then there's a video giving you where my predecessor walks through what to do with the magnet with your students. So those are both linked on this page. Great. So just a reminder, I love this slide, just talking about how nano is just everywhere and everything, and it's just touches on any area of science and technology you can think about. All right, so I did want to also introduce these two new slides, which I got recently, which I think could be really used to attract your students in talking about why this area can be valuable to them. And it's that idea that without this whole concept of nano and fabrication, these things would not exist. And even if they don't know what the names of a transistor is or a chip is, they know these names. Okay, so without this technology, you don't have Google, you don't have Netflix, you don't have Apple, you don't have Sony, right? You don't have the PlayStation, you don't have any of those things. So I really like this slide. So I wanted to make sure to share it with you, and you're welcome to use it. SEMI is the group that I got it from, and they're happy to have teachers use the slide. As well as this one, talking about how innovation has changed from these old school computers that took up rooms to, you know, the personal computer, which they're going to laugh at when they see if they haven't seen one yet, to the, you know, the 90s, my time, and the introduction of the web, and just how far we've come to now where we just take for granted this smart world. And it's just pushing forward. And this is really an exciting time to be involved in this industry. And then it just kind of, you know, gives some examples. Take a look at that later. I like this one because it's just talking about jobs and money that is current in terms of 2025. We heard of the CHIPS Act and all this funding being put into workforce development, and that's continuing to happen. But it's nice to see some dollars associated with that. So that's, I thought, might be a slide you might have a discussion with your students about. This is one you've seen previously. This is just about the applications, but pared down to maybe some smaller areas instead of having so many on one slide. Might be useful again to talk about with your students. So now let's get to the nitinol activity. So those of you that have the nitinol, great. If you don't have it, that's okay too, because like I said, it's a really, really simple activity that you can do. And if you don't have the materials now, it will literally take you less than 5 minutes to play with it once you get them. Okay. Okay, so I'm going to walk through just sort of an introductory lesson that I used with my high school students. You know, anywhere from 9th grade to 12th grade, it's the same thing. So we're going to watch a really brief video clip, and I'm going to turn off the sound, so I don't want you to hear the sound. And the question here is, how does it move? So I want you just to take a look at the video and think to yourself, how is this thing moving? What's happening? And give a description of what you see, 1 to 2 sentences. Okay. So anyone want to share how they would describe this kind of movement? Yeah, exactly. You guessed it before I even says, yeah, it looks like a worm. We have Emily saying she thinks maybe magnets. It looks like it's alive, contracting and expanding. Any last thoughts before we move to the next one in terms of how it moves? Oh, I missed this one. Solid state transitions. Okay. Lots of fancy words. We'll see what that means in a minute. Maybe temperature is influencing the movement. Okay, great. Thank you. Good ideas. So let's go ahead and now we're not going to watch you again. So now we're going to watch it again. Oh, Lucretia Electronics. And now instead of focusing on just what is the movement, thinking about what's causing that change, what's causing that movement. So now we're watching the same exact clip, but having a different focus in terms of what we're looking at in the video. And again, sound off. So what is causing that change, that movement that you described? And then, yeah, then you can go ahead and put in the chat or undo. So we have electron distribution, phase changes with Miller planes. I don't even know what Miller planes are, so that's great. I think, yeah, Lucretia had said electronics. We had temperature as one. So I'm showing you a little bit more of that video. Yeah, and then we have the temperature change. Okay, so all good ideas. So we have some different inputs, right? And this is an opportunity to talk about like different types of energy. Okay? That energy has many forms. And so this could be a gateway into that topic. So there's actually a specific material that's allowing this change to happen. And that material is called nitinol. So Ni, short for nickel, Ti is titanium. So it's a nickel titanium alloy, nitinol. Now I wouldn't tell the students that, but I'm just telling you that. So it's just, we have this, we just call it a mystery material. I don't even necessarily tell them the name because then they'll be Googling it. But the idea is first to start with just observing that material. So I would be giving my students something to compare it to. So that's why the idea of a paper clip. So I would have them compare just a simple paper clip, which I'm going to go ahead and unpin Nicole. And sorry about that. And spotlight my little dish that hopefully you can see. Is my little dish spotlighted? Yeah, so there is the paper clip. And then those of you that got your nitinol material, you got a strip of this dark looking material, which hopefully you'll be able to see on here. Okay, so from far away, they look very similar. Okay, so I would ask people to take observations about them. So 3 observations of these materials. So you might, what's a property that we could make an observation about? Okay, so I see, it looks like it can bend. Yeah, black. So yeah, definitely color. Oh, thinking about, is this the same material in thermostats? Okay, interesting. Yeah, so it's the black is the nitinol is definitely more of a black color if I put these two together. My paper clip is a little more shiny. Um, and then I see Krista saying flexible, dark and thin. So this is where, yeah, we want students to like feel like moving the nitinol back and forth compared with trying to move a paper clip back and forth. So we want to encourage them to use all of their senses. That's why I have that 5 senses thing up there, except of course taste, right? We don't want them putting it in their mouth. But the idea that, yeah, you might even smell it, right? But you definitely want to feel it. You want to touch it. Okay, and get a sense of, different observations that you could use. Yeah, does it snap or bend nicely? And there's a fancy term for that called malleability, if you want to talk about that. Oh, does one feel heavier? Ooh, good question. Yeah, that's, you kind of like put them in your hand and see. That's one I actually really haven't thought about. Yeah. Anybody have thoughts? Anybody have a paper clip and nitinol? And can hold them and see if it's discernible which one they think is heavier? Because I have a thought, but I'm not confident in that observation. Oh, reminds me of bread ties. Oh, interesting. Okay. Well, based on my very unsure observation, it feels to me like the paper clip is heavier. But I'm not super confident in that observation. So then I would also encourage people to take a pencil and try to wrap both of them around it. And this will help them tune in on the how flexible is it and how inflexible is it. Because if I take my nitinol and I try to wrap it, it's pretty easy to do. And then I can pull it off and, oh, look, I made a nice little shape. But if I try to do that with my paper clip, it's really hard to do. Um, and it doesn't quite take the shape as well. So that's what the pencil observation is for. And yeah, so I like that Mark's already jumping to the question of, does one feel heavier? So that's a great question. Does it snap or bend nicely? So you're definitely asking those questions. If you added water, would it keep its shape? Okay, so wanting to have and interact with other environments. Yeah, great. So we'd have, students share out either in small groups or in a larger group. But what's nice is this material is very safe and easy to use. The only thing you want to watch out for is that the paper clip, if they're trying to bend it, it might actually kind of fling away. So just, when you're thinking about safety, because as a chemistry teacher, I always think about safety, giving that as a warning. Oh, asking about how fast does it react? Does it conduct electricity? Great questions. Okay, so then hopefully some of these questions would lead to this concept of let's try using different energy inputs to see how the nitinol behaves compared to the paperclip. So this is where I would have things around the classroom for students to use. I would have, a bowl of cold water, a bowl of room temperature water, a bowl of, warm water, maybe water at different temperatures. And they could go around and try things. You might have a station set up with a hair dryer, because that would be heat, because some of you mentioned temperature. So you're giving them different ways to try that. You can use electricity, but there's a big warning to that, because the material gets very, very hot, and you also will short out batteries very quickly. So especially in an exploratory situation like this, I would do that maybe more as a demo with you leading it rather than having students do it. So just as a first thought. Okay. So, oh yeah, great. Yeah, your hand. Like, what about your body? Exactly, using your body heat. So taking that nitinol and rubbing it between your hands and seeing if that makes any difference. That's a great thing to do. So, what I would do next with you guys, in case for those of you that don't have the material yet, is I actually have my hair dryer set up. And that way I can actually try applying heat to both of these materials and see what happens. So, because when I tried this, it went flinging everywhere. You can also buy nitinol in really long wires and cut it up. It's the cheaper way to do it. So I'm going to use my long wire just because it won't fling everywhere, because I had that problem yesterday where I was searching around trying to find the piece. But I'm going to take my paper clip and I'm going to go ahead and heat it up. So I counted to 10, and did anything happen to my paper clip? Did it look like it changed in any way that I could discern on the camera? Thumbs up, thumbs down. I see faces going like that. Yeah, no, thumbs down. Yeah, no change that I can see. So now I'm going to move my paper clip off, and I'm going to put my long piece of nitinol, and I'm going to do the same thing. I'm going to count to 10. So did everybody see that? I was trying to hold it as it's wiggling everywhere. So was there a change? And can you describe the change that happened? And it's very obvious that it absolutely did change. And it changed drastically. So this is when the questions start pouring in from students, right? When they see this, it's like magic. It's this amazing thing that happens. And so lots and lots of questions about what can happen with this material, what are applications, then they start wanting to try different things. If you have warm water, it's instantaneous. Like you literally just dip it in and bam, it changes right away. So if any of you had any of the warm water set up that have nitinol, it's pretty crazy to try. Okay, so then this brings it to now we want them to kind of like what you all have already started doing, which is start to internalize it and really think about like, what does this remind you of? We saw that someone mentioned already about the ties. What do you wonder about it? How might this material be useful? What doesn't seem to work with it? So the idea when you had different, like, for example, temperatures of water set up around the room, okay, because it has to be, and you can even with your hair dryer, you could do different settings on your hair dryer and try that out and see what happens. So there's all these different ways for students to pretty easily explore with this material, which is why I really like nitinol. If you want to build like a more activities around this, you can also buy different types of nitinol that are pretty inexpensive. So this other type, this is nitinol that I have. Sorry, I'll put it on here. That you'll notice hopefully you can see it. It's more like a spring. So I'm going to go ahead and pull this spring out, and I attached just a lump of clay to it, just as sort of like to use it as a weight. And then I'm going to do the same thing that I did before. I'm going to apply the heat to it and see what happens and see if it can actually, because that's one of the questions that always comes up, it seems, with this is like, can it pull stuff? So let's So yeah, it can pull that chunk of clay, no problem. And so it's really just something that's stirs curiosity and actually also creativity and innovation, which is why nitinol is magic sand and nitinol are two of my favorite nanomaterials. So these springs are kind of the opposite in some ways of the other nitinol material, right? Because when I applied heat to this one, it curled up. When I applied heat to my long string, it got straight. So this is what's cool about nitinol is you can actually customize what you want the nitinol to do. And in fact, you can train the nitinol to have different shapes using just a candle. So that I actually had a student who asked his girlfriend to prom with nitinol. How awesomely nerdy is that? And he showed it to me. He was so excited. I'm like, that is just amazing. I love it. So it is a very easy to use material that can be changed with pretty simple tools. Yeah, it's the best story ever. I love it. Of course, he became an engineer, but still, that's all good. So let's zoom in on this material now that we've had our playtime, because right, the whole idea about playing with the materials is for students to get curious, to build interest, so that they actually want to learn something about it. That's the whole point of this. And if you have time in your classroom, you can also have innovation challenges, right? Challenging them to think about, what do you think you could do with this material? We had a problem in my high school for a while of engineers can be right, of car crashes into light poles. And for some random reason, by our school, we had several like light poles that had gotten hit and fell over. And so I had a student that built this prototype of a light with nitinol infused in it, so that if someone ran into it and it fell over, could they just apply something, the energy to it, and just make it stand right back up? And they used clay as their model, as to add weight, to see what the point was at which the material couldn't get back to its original shape. So really interesting and simple project using clay and nitinol and looking at what was going on in the world around them. And I think that that's the best of any type of science experiment, right? Is one that is from natural curiosity. But I could talk all day about the stories of nitinol. So stop me, Jenny. If I keep going, you gotta stop me for time. But we'll move on to the actual nanoscale part of it. So if you take a look at these images, right, we want to look at them and think about how they are different and maybe how they're similar. And it's martensite and austenite are the terms. Okay. So take a look, and again, you can talk or you can put in the chat, whatever you want to do. What do you notice in terms of similarities and differences? And maybe you might, have your students do a T-chart or, whatever are the strategies that you use to help them learn. Oh my gosh, I'm dying right now. There's over 20 of you here right now. I am just amazed. You guys, I'm telling you, before we've had like 6 or 7 people show up if we were lucky. So I'm just, wow, makes it all worth it. I'm so excited. Okay, but I don't see anything in the chat. Oh, there we go. Okay, so so looking at a difference in the martensite, the nickel is found at the junctions. So the nickel is the big gray, and it's found kind of at these junctions, meaning where you have the 3 intersections of that line. Yeah, okay, absolutely. Or an exterior, yeah, martensite has the exterior nickel. Let's see, we have one describing austenite as a linear crystal. One is at an angle and one is 2 on top. Oh yeah, in terms of the nickel, yep. Yeah, looking at 90-degree angles. So the austenite seems to have these 90-degree angles. Yep, great observation, everybody. Lots of interesting, focusing on, yeah, how the nickel versus the titanium is distributed. Great, all right. Unequal structure versus equal. LaQuisha, would you mind elaborating a little bit on that, what you mean by that? What is unequal versus equal?
I was just talking about the 96-degree angle on the
Oh,
Martensite versus the 90-degree equal 90-degree angles on um
great.
the other one,
Yeah,
austenite.
I think it's interesting that you use the word equal though to describe. So when you're talking about equal, is equal is the 90 degrees? Is that, I just want to make sure
Yes,
I'm being clear. Okay.
yes.
And so yeah, honing
And
in,
it's Lakeisha, guys.
yeah, Letitia, yes. LBJ.
Yeah,
So
thank
yeah,
you.
looking at that angle, thinking about it in terms of like an equal structure versus an unequal structure. Stacked, I see this description from Krista about stacked material. These are all really important. And then the question is, yeah, how does that connect to stability in terms of which shape we think is the most stable? So this is really why we want to look at the shape, because we want to understand the stability of the material in terms of its crystal structure. So we can just do a thumbs up, thumbs down. How many people think that the martensite is the most stable? Thumbs up if you think martensite is the most stable. Okay. Thumbs up if you think the austenite is the most stable. Okay. So it seems like a lot of people, some of you have the update that's doing the thumbs everywhere. So it looks like austenite is the one that people are really thinking, yeah, that's got to be the one that's the most stable. All right, interesting. Let me make sure I didn't miss anything on the chat. Okay, and yeah, I should clarify most stable like at room temperature. So it like, just normal room temperature, which one's the most stable. So that brings us to, let's think about that. Which shape do you think would require the most energy to be changed? So this is another way to ask about stability, but you're asking it in a little bit different of a way. So which shape do you think requires the most energy to be changed? Okay, and then, oh, I gave that one away, huh? Okay, so connecting this to stability. So I passed by this part saying that the martensite is actually the most stable, which is surprising, right? Everybody said the austenite. And this is my analogy for that, is that 90-degree angles are very costly in terms of energy. If you look at nature, how often does nature do 90-degree angles? Do rivers run at 90-degree angles? No, right? They meander and waver. So this idea of rigidity of 90 degrees is very uncommon in nature because it is very energetically costly. And the analogy I give to students is when you're sitting in your chair on your computer or you're just standing in general, how are you standing? Are you standing with good posture and a very rigid structure? Or are you standing with your shoulders hunched over and your knees bent and just kind of like relaxed? We all know we're all doing it right now. We're sitting relaxed, right? We're in the martensite version of ourselves because it's just easier. It's less costly in terms of energy. If I want to have good posture and be rigid, right, that's going to cost me energy. So that's my analogy for that. All right. So now thinking about which requires the most energy to be changed, we know that martensite, again, at room temperature, is the most stable. So if I want to change it, how much energy has to be put in to make that change? And we refer to austenite as the high energy version. Okay, remember, we want to be here because it's really easy and doesn't require a lot of energy. So in order to get here, rigid, I need more energy. That's why it's referred to as the high energy structure. Okay. So I'm going to check the chat. And yeah, Pilates. Does anybody have any questions about that? So this is getting at how structure relates to function, right? So we want to go for big ideas if you're thinking about NGSS or other things like that. Yes, Earth Science Connection, exactly. It's an interesting way to talk about crystal structure that students can see, like how that impacts different properties of materials. Yeah, it's great. Okay. All right. So I think we already talked about that. Which one is the rigid form? It's going to be the high energy. So when we have the nitinol in our hand and it's just sitting there at room temperature and I can do all sorts of squiggly things with it and whatever I want right now, it's at the martensite version, right? It's easy to manipulate. It's very stable. So I have to put in energy with my hands to make it change. Okay. But as soon as I get my blow dryer and I put that on here, I'm adding energy to the system and I'm actually shifting that crystal structure. I'm putting in energy to shift it. And that's why it goes back to that high energy form. And when you try it, you'll see it's very, very rigid. And then as it cools, it relaxes to be a little bendy again. So you'll be able to observe the whole basically phase change. Bad Daniela. The whole change in the material happening with it visually, which is pretty cool. Okay, so in terms of how does this material change with energy, these are just more ways for your students to actually do like a word where they can take words and assign them to the different pictures. So you could take heat and decide which one. You could use this as a formative and as a post assessment, just having them put words under which structures they think make the most sense. Okay, and then this is this is an example of kind of like the ideal that they would end up coming up with, is that this is a physical change, it's a phase change. It's not a chemical change. And then you know, all the things that we just talked about, like where you have to put in heat when it deforms and so on. Okay. And I would compare this to the water cycle if you want to talk about phase changes, because students know solid, liquid, gas in terms of water. And you can connect it to a phase diagram if you so chose, thinking about, you know, where phase changes occur and where you have a phase change that's very unfamiliar. This is a traditional one where you see like solid, liquid, gas, and what the particles are doing. So if you teach about that, you can really use this to connect to phase changes. So I'm more than happy to give you more information about this, but I want to make sure to get through it. I'll just click through these. There's some explanation about what's going on. Basically, when we add in that energy, the temperature does not change at the moment of a phase change. The energy is used to actually shift the atoms, to shift the crystal structure. So when you have a phase change, that's why it's on the flat part of the diagram. That's why you're here, because the energy, the temperature, the kinetic energy is not changing. The energy is being used to break bonds so that you can allow for a shift. So that's what's going on in terms of the chemistry. All right, so we're going to go through that. One application I threw up here was disease diagnosis. It has to do with some nanowires of nickel and how they change in response to blood platelets. And so this is an interesting example that was done at Georgia Tech, one of our partners. You can read more about that. The video you can watch on your own. It goes into the explanation, but we're not going to have time to do that now because I'm already behind. And then I also like to mention the art connection. Artists actually use nitinol to make kinetic structures. And this is one of my favorites because it goes from, basically it's French for despair when it's cool. And then as the nitinol heats up, the mother raises the baby and it's like, you know, joy. So you're going from like despair to happiness or joy. So it's pretty cool. So I like to always mention the art connection. Okay, stop talking, Daniela. Now I want to give teachers an opportunity to share out what they had done. So I asked those people that had been here and had told me that they had implemented, if they wanted to share out what they did. And you will also get a copy of this. So this was the template, and I'm going to jump forward to letting Dr. LBJ, why don't you share with us about your slide? And you're first.
Good morning. I didn't really get a chance to work on my slide in detail as I wanted to, but I just wanted to highlight the best that I could, what I had done thus far and where I'm headed. So when I was at the summer workshop, I started thinking about or conceptualizing a unit around science and the world around us and teaching measurement, inquiry, lab safety, etc. And so the first one that I did, Nano Lab, I did was I introduced the thin film lab as a way of getting to know the students. And so I just shared like a little bit of what nano technology was with the video that was linked in my slide. And then I also told them about my personal experience with nano and stuff at Stanford. And then we did the surface area lab next, and we did more with PPE, lab safety. We had, wore our goggles and everything like that. And then after we completed that lab, I had them do I wonder, I notice activity. And then I noticed that a lot of them, either they verbally discussed what they thought, shared their thoughts verbally, and then some created models, which was directly connected, with the standards. And so I thought that was pretty great that they didn't necessarily ask for a model, but they gave me models. And then some gaps, I said that student understanding of concepts, of course, of nano itself and kind of hearing it for the first time, but it's one of the first things they've learned this year and they remember it. And so they always, when I mention it or they mention it, they know what it is. Just the time to implement nano into like life science, because that's my major area. And then lesson connections in that, uh, kind of more thematic or more integrated science connections. And then future plan to implement more nano labs throughout the school year. And the two that I'm looking at doing next is the lithography, both the sun print and the chocolate.
Awesome. Thank
And I
you.
was gonna include my pictures or two, but I couldn't find one of them. And then I just didn't have time to black out faces and stuff. So
Yeah, no problem. No problem.
thank you for letting me share first.
Absolutely. And thank you for providing a link. So anytime if you're sharing and you want to put links, that would be great because I know we all like to, as teachers, don't want to have to reinvent the wheel. So if there's something like a framework that was helpful and you put it in here and you were willing to share that with people, that's always wonderful. All right. Nicole, I know you started telling us a little bit about your experience, but why don't you go ahead and now you can use your lovely slides to show us.
All right, so these are pictures taken from the SEM workshop that the scientists at University of San Diego shared with us. So I started off the school year with units of measurement. I introduced the metric system to them, and then we followed up with the card sorting activity. And what was really sweet with the card sorting activity, it was cool because this was right at the beginning of the year and the kids were coming into the classroom and they're like, wow, we're really doing science in science class. Because again, they hadn't had a science teacher in such a long time. So they were so hungry for it. And then that led into, we were talking about positive and negative exponents. The card sorting activity was really good with that. I also, before the card sorting activity, we watched the Powers of 10 video too. So that did a really good job of, again, reinforcing what a positive and negative exponent like represents or symbolizes in terms of size. And then I reached out to you because I was trying to get in touch with the Hitachi folks, and yeah, they were unresponsive. But thank you so much for linking me up with the Nanotechnology Institute at San Diego. I will say, teachers, they weren't very good with working with kids. They were just like very dry. So, you know how, like, I have 4 middle school classes. So the first class, it was kind of like my rough draft performance. And I realized by the second class, I'm like, I need to facilitate this. These scientists have no clue what they're doing. So I turned it into kind of like a I was like, all right, you guys, you can only ask me yes or no questions. So it was basically, honestly, you don't even need to link up with the SEM folks. Just ask them to send you a bunch of photos and put it into your own slideshow. What was nice is if you look at the bottom of the pictures, it shows you the scale and it shows you the size of like how many times magnified it is. So that was pretty cool. And then you don't really need to have this workshop. Just have them send you a bunch of photos, put it in order on a slideshow as you're zooming in, zooming in, zooming in. And then you can probably facilitate a better workshop with your own kiddos than the scientists can. So what I did was I had them, like by the time I got to my 4th class, then it was fun. Then I was like, all right, I know what I'm doing. So I was like, you can only ask me yes or no questions. And then they were starting to get good. They're like, is it alive? No. Is it so biological or human made? The slide at the top on the right there, they thought that was COVID-19 and it's pollen. And then the slides as they went on zoomed into the structures on the pollen, which helped to attach. And then, yeah, with the butterfly wing, that's the bottom left, we could see the nanostructures, and then the bottom right is shark skin, which is really cool with bacteria clumps. So they were able to see that when you rub against shark skin in one way, it's smooth, and the other way, it can actually cut your skin. It's kind of hard, rough. And then I included an interesting quote. It was really cute. One of my students, Cameron, he was like, wow, I feel a lot smarter after this workshop. So it's pretty cool.
And I think you bring up a good point, Nicole, that, and you can send them samples usually if you connect with them, is sometimes just knowing that scientists help produce the images can be really helpful, because it might be hard to get them to do 4 or 5 classes. But if your students can send them the actual samples and then they get pictures back of the things that they chose, that can be equally powerful. And even I think it's good feedback too to I hope you let them know, like through the RAIN network, that it would have been nicer if it was geared toward a little bit younger of a student. I think when you're requesting for people, because there's some great people in the network, because it's lots of volunteering, and there's people that maybe have a little more trouble communicating, is give them a really good description. Be like, I have middle school kids that don't know anything. They really need to have. Did you? Okay, yeah, and I'm sure. Yeah, I just want to make sure.
I think the other thing that was difficult is they weren't on screen. It was just the slide. So they were like, the kids are asking, how tall are you? What do you look like? And there was no, it was just interesting. But I think if I were to redo this, I would rather just send samples, send me pictures, and then I'll create the lesson.
Then you can do it. Okay, that's great. That's good feedback. And I will definitely send that forward as well, that maybe having them on Zoom, and because I think it is important to see the face of the person that you're working with. Okay, time-wise. All right, Debbie, you're up next. Thank you, Nicole, for sharing.
Can you hear me?
Yes.
Okay, I promised to go fast. We got a great time. I work with kids who have learning disabilities, so I was thinking I was going to have to help them through a lot more. And I was ecstatic to see them do more things independently. I think the funnest thing was the sun print activity, where they started with the little films, but then they went outside and found rocks and paper, leaves from different trees, and they just had a blast with that. And I think the best part was in the end, I had them do little slideshow. That's what I have on the, like, little pictures of a slideshow of different jobs that involve using nanotechnology. And they said, wow, I could actually do some of these jobs. You don't need a degree to get these jobs, and you don't need to be able to do all these really hard things, but these are good paying jobs that I can do. So that was exciting.
Great. And if you're comfortable with Debbie, I'm sure people would love to see a link to your slides.
Yeah, I think
in there. That would be great.
Okay, I'll add it. Yeah.
Perfect. And I really do love the career connection piece to it, because that's so important for students. All right, great. Aditi.
Hi, good morning, everybody. So I'm a 7th grade science teacher in the Bay Area. So I started with our nano journey. by introducing the card sort activity, because we started with the atomic structure of matter. So yeah, so it was very fun for them because they were learning about exponents and negative and positive exponents, and they were able to understand atoms versus nanoparticles. So that was the first introduction where I gave them what are nanoparticles, because the word nano they knew already, but nano was around us. It was very new to them. And so they got pretty excited. So then we moved on to learning about physical and chemical properties. So they did a little bit of chemical reactions also. So then we talked about self-assembly, and also did the like the sodium alginate, alginate and calcium chloride thing, and it was pretty fun for them, and they played around there with that. So it was very, very fun. In fact, I also loved that, and I wanted to, as a part of, again, as an after-school activity, try with fruit juice and make a real boba kind of thing, the sweet assembly. So we are actually planning for that. But the one which I have put up here is about the surface area to volume ratio, which was kind of in our district, we are actually working with CSU, East Bay, and to enforce more math and CERs. So that's why I wanted to just share with you also. This was very much a little bit math oriented, because they wanted to, I wanted to introduce the concept of surface area and volume to them, and which was pretty new. And I found that many of them were struggling with that idea of what is volume and what is surface area, so calculating those. So then I gave them like it was a group activity, like we had at least 8 groups in every class. So each group had 4 to 5 students, and I gave them a pair of like 2 graduated cylinders with like the Alka-Seltzer and the crushed ones. So they were to observe and write a claim where in which cylinder they saw the reaction was faster, and then they have to know the data. That's where I found that it was struggling for them, because they were able to know the fizz height. It was like they could note it, but taking the time thing, which I think I will help them more on that, so that they can get that data in that evidence. And the reasoning, we already did a little bit of math. Then I said, use your, like what we like just did before, to calculate the surface area to volume ratio with it. So that is what is the reasoning part. But I think we have to do more and more of that in order to get them understand, because the CER is kind of new for 7th graders, because they come with almost no background of science, just as Nicole shared, is also the case in this district, our Hayward district too. So we are trying to support as much the students as I can. But CER also is a very important component of the CAS test, because we think that they take it in 8th grade. So we are pushing that, but I'm really happy to share with them that this nano technology and CER, how we can all it can be embedded. The CER was embedded into this nanotechnology lesson, and I could do it, but I would love to do more in nano, because I want to also introduce about the magic sand activity, which was really nice. When we do the natural hazards, I want them to do a project with that. So that's my goal.
Fantastic. Thank you so much for sharing, Aditi.
Thank
And I
you.
just wanted to, just because time-wise, and it's very much my fault, let everyone know that it's 11:02, and if you have to peel off, I completely understand. I am going to follow up with the 2 links to the resource pages, the links to these slides, as well as a post survey, if you can fill that out for us from this workshop. Mariana and Michael were still going to share, so I want to give them the opportunity to do that, but I also want to acknowledge that if you have to go, please, your time is valuable. Please feel free to step off. And I will be following up with that email. So knowing that, Mariana, if you want to go ahead and share with us what you did, it'd be great.
Oh, hi. What I did was I really wanted to show a way for my science department to incorporate nanoscience without having to be experts, because none of them went to the workshop with us virtually or in person. And so we had to make a project, and their goal was to put some nanoscience into their project somehow, anyhow. And so I used the Nanos magazines. We were studying energy, so we all looked at the energy issue. And then there's a handout here that you can see there. I put a link to that handout. It's like a Google Doc into the notes, but we filled out like the first row together about energy. And then in their project, they look through all the other issues, and it's kind of like a jigsaw, like a modified jigsaw for them to look at the other 4 issues. And then they talked to other people who read issues, and then they thought about ways to put it into their project. And then while they were making their project, I pulled one person from each group so I could hear what their project was, their idea, and how they were going to incorporate the nanoscience into their project. And it was completely creative. And that's one of the reasons I loved it, is like, they were like, well, there's these nano generators, and they use like nano wires and nano sensors. And so it was really a great, easy way for kids to jump in, and my colleagues to see that you don't have to be an expert. You don't have to do all this stuff, because you're not the source of all the information. It's the magazine. That's it.
Great. Thank you, Mariana.
Sure.
This pulse power. Wow, that's so attractive. Those are wonderful artists with that one. Oh my goodness.
Yeah, they love it. And then those are models down there below, like glasses, and then right there. And then there's one on the right one. There's actually a contact lens they were gonna like put in their eye. So when you blink your eye, that's the kinetic energy it gets. And so they just went like nuts. And so I just told them how inspiring it was. They were so creative, because it's gonna take that to help us solve all the complex problems we have.
Absolutely. That's amazing. Thank you. Now, you said you put the link you're going to put it on the slide?
No, it's
or?
in the notes of the slide. It should be right
Oh,
there.
in there. Okay, perfect. All right, great. Thank you. Okay, Michael, you'll wrap things up for us.
Good morning. I wanted to share my thin films lab that I implemented as a part of my PBL unit that integrates nanoscience with computer science education. The thin film lab was used as like an entry event. This is like the beginning of the year where kids could get creative, even if, they don't have that prior knowledge. I followed up the Thin Films Lab with the size and scale activity to help reinforce students' understanding of how the wavelength of visible light is the same thickness of the thin film. They expanded this concept when they did the chocolate lithography lab, where I introduced the difference between physical color and chemical color. The physical color is the diffraction grating, and the chemical color is the chocolate itself. Students explored properties of electricity and magnetism using a snap circuit. They're these little kits that you can get, where I just showed how electricity is conducted. They did one of the semi assignments where they researched a couple of companies and how nanoscience is implemented in terms of careers and the education prospects associated with them. I had them basically write a short reflection about how thin films are used in electronics, and connected that, hey, we made a thin film in class. The culminating project to this unit is they will be given a microbits computer. It is to show them just the basics of circuitry and how thin films and these ICs are used in computing. And they're going to make a Scratch program that gives them an introduction to Java programming. I have found that a lot of students really enjoyed the hands-on learning. There were some students where they were able to get very creative with the name tags that I've showed on my unit. I did a link to the PBL unit because there's a couple of things I still want to implement, such as the microsand to help support their understanding of like hydrophobicity. And I also would love to try and get maybe some of the SEM images so they can really see what nano is like. And Next Metal, they have like all sorts of nitinol products that you can buy, and they're like $7. You just for a meter, I think. But thank you for listening to my talk. I
Awesome.
really enjoyed the workshop.
Yeah, I know. Thank you, Michael. This is really interesting. And I think seeing how each one of you put this into your classroom in different ways, it's such a great variety. I mean, it's by far the most that we've seen in teachers sharing out. So you all, wow, like A++. You guys are living up to the expectations and beyond. So that's amazing. And I also just want to, because the SEM has come up several times. So I had mentioned that we have the SEM at Stanford, and Karithika actually just helped me roll out a test case last month where she sent me some samples. I slapped them into my SEM. I turned it on at 8:30, walked away, gave her control through something called remote PC, and she ran the tool with her students the whole day. And then at the end of the day, I came, turned it off, and left. So it was, because I can't take a whole day to walk through for students. But because she had experience with the SEM, which isn't that much, we met one time before, did a quick remote, how to use it. And then it went shockingly well, right, Karithika? We were like, oh, this worked. The Wi-Fi was good that day. But I think my plan is to start, and since you all are here and you stayed longer, so this is like your bonus, that I'm going to try to have where once a month I will have a slot and teachers can sign up to use that. If that, I'll say, here's 2 days, I'll set up a calendar or something, and you can sign, it's kind of like first come, first serve. And then you can run the tool with your students, and you can, if you can just mail me the samples and I can put them on. I think it's something that it would really be a way for you to bring that to your students in a way that you can control, like Nicole was saying, to make it as impactful as possible, but also connect it to saying, hey, here are these people at this research university that care about you interacting with this, and they're taking the time to give you, control of this tool that other people are having to pay to use. Because researchers are using my tabletop SEM for really simple checks. So they would actually be using a tool that Stanford researchers are using, which is pretty cool. So yeah, so if that sounds interesting to you, when I send out the email with all the stuff, you can send out an email and say, hey, Daniela, I would like to be part of the pool of people that can try to use the SEM with students. And then I can just sort of see how many people, and then figure out, and at least try to do one a month. So that would be like January, February, March, April, May, probably June. So probably 6. Okay. Awesome. Well, it is now 11:11. So I want to thank you all for coming. It's great to see you and to hear from you. And I hope your year's going well and you'll have a wonderful vacation. And if any other questions come up, feel free. So tell me if I missed anything, because I wrote notes. I'm going to, in my email, follow up with the 2 resource page links, a copy of the slides I showed you, including the slides to what the teacher just shared out. And then I'm also going to ask you to do the post survey. Was there anything that I missed that I want to make sure to put in the email? Nope, looks good. Awesome. Okay, great. Well, have a wonderful weekend, and look forward to staying in touch with everybody. So